26. Problem 26. Hypergeometric distributions. Binomial experiments require that any sampling be done with the replacement because each trial must be independent of the others. The hypergeometric distribution also has two outcomes, so it's a binomial, success and failure. However, the sampling is done without replacement. So this is a different formula. Probably won't put a whole lot about hypergeometric distributions on the test because this is the only problem we've done the whole chapter that's dealt with it. Given a population of n items having k successes and n minus k is the failures, the probability of selecting a sample of size n that has x successes, n minus x is the failures, and they give us this formula. Px equals, somebody help me out and read that to me. Close the parenthesis.
N minus K, C,
N minus K little.
capital N minus.
Everything's little tits.
C, then N. Little n or big N?
Little n minus x.
Little n minus x.
And then close. Over little n big, or big, it's big N, but like it's a little one. Big C,
Oh, okay.
and then lowercase small n.
So what we need to do first on this is read what it says there, and we're going to find all these things. We're going to find big N, we're going to find K, we're going to find little n, we're going to find x. I think that's all we need, isn't it? So it says in a shipment of 15 microchips, 2 are defective and 13 are not defective. Well, I'm not sure why they told you 13 are not defective. I guess they think you're not the brightest of people, so you couldn't have figured that out yourself. A sample of 3 microchips is chosen at random. Find the probability that all 3 microchips are not defective. So we want the probability that all 3 are good. Ignore that stupid straight line there. How many total microchips do we have? 15? How many K is, what they say K stood for? Successes out of all of them, right? How many successes do we have?
2.
Be careful. Other way. 13. Because we want them to not be defective, right? Then they say that we're picking how many at a time. We're not picking all 15 of them. How many?
First one's
3. So we're picking 3. Now, how many are we?
The 3 aren't defective.
So we're
A
picking.
sample of 3 microchips is chosen at random.
So we're choosing 3 each time, right? We're saying, okay, I'm going to pick 3 out, look at them, I'm going to pick 3 out, look at them, I'm going to pick 3 out of the 15. So we're picking 3. Now, what Lucas was saying, how many do we want to not be defective this first time?
The 3, all 3.
The 3. That's going to change for each problem. That's going to change for part A, part B, part C, however many parts there are. So all we're going to do is plug in all these numbers. Have your calculator out to help me. We're going to plug in these numbers. I'm going to use that bar there as my fraction bar. We're going to punch in 13C. X this time is 3, parentheses. N minus, big N minus K is 15 minus 13, which is 2. C, little n minus x is 3 minus 3, which is 0. Big N is 15. C and little n is 3. So we're going to find all that. Now, if I was doing this on my calculator, what I would do, I'd find this number, write it down, find this number, write it down, find this number, write it down. So what's 13C3?
286.
286 times what's 2C0?
1.
1.
How do you get the C?
You go to math, then go over to probability.
It's number
Oh,
3.
okay, I see.
Remember, you gotta put in the number first, right? You gotta put in the first number, then go to that, then put in the second number. And 15C3 is how much?
455.
455. Anybody else get all those numbers or just Miss Clark?
I have 286.
You can get none of them, Jacob?
I couldn't find the thing until you just said it.
So you remember where it's at now?
I'm trying. Yeah,
That's what you got. So what's 286 times 1? That's not real hard. 286. Then we're going to divide that by 455. So just 286 divided by 455. 628. So if we got these 15 microchips in this box right here, and I tell Camden to grab 3 out. What's the probability that he's going to grab the 3? All 3 of them are going to be not defective.
62%.
About 62 or 63%. That's what we're saying with that. Part B says 1 microchip is defective. So this time we want 1 of them to be defective. So how many are not going to be defective? 2. 3 minus 1, right? So we're going to do all the same stuff. The only thing that's going to change is our X. So we got, couldn't find the C on your calculator before, be trying it now. The K is going to stay the same. The X is going to change this time. It's going to be 2. N minus K, that stays the same, so that's 2. N minus X, this time 3 minus 2 is just 1. Over, down here, that all stays the same. So do you need to do the bottom part again? Hold on, does that stay the same? Yeah, that's an N. What's the bottom part? 455, it's going to stay the same. Oops, I put K. Why'd I put K? What's K supposed to be? 13, that was stupid.
It's
78 for the first one. Anybody else get that?
Yep. And the other one's 2.
The other one's 2. What's 2 times 78?
156.
156. What are you going to do with those 2 numbers? 0.34. So what's the chances that Cameron sticks his hand in that box and he pulls out 2 that aren't defective and 1 that is? About 34% of the time. Next question. Just looking at mine to make sure I just did that right. 6. Oh, there was another part to that, wasn't there?
Yeah.
Sorry. Part C. I'm not going to do all of part C. Is that all right? Part C is we want probability that you pull out 2 defective, and I think that's what it said. Let's see. 2 microchips are defective, 1's not. So what's probability you pull out 1 good one? I'm just going to give you the percentage. What do you think should be true about this percent? That Camden's going to stick his hand in there and pull out 2 defective and one that's good.
Should be pretty low.
Should be pretty low. What do you notice about that probability? It's about 3%. What's that tell you? Is it very likely that Camden's going to stick his hand in there and draw out 2 defective ones? Probably not. Remember, if it's less than 5%, then it's unlikely that it's going to happen. That's about 2 or 3%, unlikely it's going to happen. You said number 6? Yes, no, maybe?
Yeah.
Number 6 says assume Poisson's distribution applies. Use the given mean to find the indicated probability. And on this one, we want to find probability of 3. And we're using stupid pen. We want to find the probability of 3, and we're using a mean of 6. Easiest way to do this one is what? Just grab your calculator. That's the easiest way. If we're going to use the formula, so grab your calculator, I'll explain both ways, since we got a test next time anyway, and you need to know both ways. For Poisson's, the formula for Poisson's is Px equals mu to the x power times e to the negative mu power over x factorial. I'll do this out longhand first. Our mu is 6. 6, we want it, this is our x. So 6 to the third times e. Remember, e is a standard number. It's always the same. It's on your calculator there. And we're going to take that to the negative mu, so the negative 6th power over 3 factorial. I can do 3 factorial in my head. That just means 3 times 2 times 1, which is 6. On top, you grab your calculator. I don't have my calculator out here. Somebody help me out. Punch in 6 to the third power.
216.
And then hit times E. Remember, E is where the LN button is, right?
No, E is the divide button for the 83.
Oh, is it?
And I thought we used that line in last class.
ln is the,
E to the power. Either one of those will work. Either one. So if you hit the second divide, that should pull an E up there. Then you got to do the little caret, right? And what caret do we want to raise it to? Negative 6. Make sure you do negative 6, not minus 6, because the calculator won't understand it. And then hit equals, and that should tell us the whole top. 0.53. Anybody else get that?
Yeah.
Jacob, you're looking confused. You can get that?
I just don't know. I divided it by,
I only have minus
I divided.
Oh, you divided?
I know the right way.
Yeah, but it shouldn't have come up an error.
Oh, I think it was different. That's the answer right there.
Oh,
That's what I got.
okay, then you click something else after that. So you should have multiplied.
Yeah.
So that's what we got. Now what's 0.53 divided by 6? 0.89. So about 9%. Remember, with Poisson's, what's that mean with Poisson's? We talked about geometric and Poisson's last time. And you got to be able to tell this on the test when I say, whatever on this problem, you got to know, hey, that's Poisson's because I know I'm doing this. What are you dealing with when you're using Poisson's distribution? Anybody remember that? You're using, it's always going to be using mean, that's true. What it's dealing with, it's saying something like a certain area or something. So we got this area right here. And we're saying the mean of cockroaches in that area is usually 6. All right? We want to pick an area and say, what's the probability that we pick that area and there's only 3 cockroaches? All right? And that's what we just found. What's the probability that we pick an area and there's only 3 cockroaches? About 9% of the time. So that's what we're dealing with there. You're always dealing with the mean, and you're picking some area, some volume, whatever length, whatever it is, and how many of these things fall in that area, how many fall in the water, whatever it is. Geometric, remember, geometric is when you're doing what attempt is the first success going to fall on. Remember when I was shooting the paper wads, what attempt am I going to make it the very first time? Other questions? 17. 17. Never get all these back together the right way. So on this one, a newspaper, and this is one we're going to have to make a decision whether we're doing geometric or whether we're doing, I think, let me read the directions here. Find the indicated probabilities using geometric or Poisson's distribution. So we got to decide. So you guys are going to have to decide for me. A newspaper finds that the mean number of typographical errors per page is 4. Find the probability that exactly 3 errors are found on the page, so on, so on, so on. So are we using Poisson's or geometric? Geometric? What's geometric again?
It's the, how many,
First success. So if we were reading the paper, we might say, how many words does it take till we get to the first error? That would be like a geometric. Here we're saying on this first page, how many errors are we thinking there's going to be in that first page? Then we turn to the second page, how many on that page? So we're doing how many errors are in that area. Does that make sense? Not going to mess that up on Friday, are you?
But, just being honest.
So it says, the newspaper finds the mean number of typographical errors. And again, Katie told us this a few minutes ago. What word in there sort of keys to Poisson's mean? So if you see that you're dealing with a mean, you're probably using Poisson's. I don't want to say all the time, but probably. So they tell us the mean is, what, 4? Is that what they said? We want to find the probability that on the first page, at most 3. Is that right? No, that's not right. Exactly 3. So on the first page, we want to find exactly 3. Instead of doing this, we're going to use our calculator. What buttons do you have to push on your calculator? What are you looking for? Hope when we start reviewing this, you guys remember this all a little better. What are we going to push on our calculator?
That word PDF. Right?
What do we hit first? Second, vars. Just about every one of these that we've done this chapter, what do you hit? Second, vars. Right? Notice second vars. At the top it's got the normal. You go down, it's got the binomials that we covered. We didn't cover normal yet. We'll cover them next chapter. It's got Poisson's, and then it's got the geo. So second vars every time. Michael remembers nothing else for this chapter. Second vars. Now Michael looks like he's got one of the new calculators. His might be different, so it's the same. So we hit second vars. What are we looking for this time? Poussin PDF. So you go down, which one is that? B. Go down, Poussin PDF, hit enter. What two things do we put in for Poissons? Put in the mean, and then the x. Oops. Then the x. Mean, then the x. So that's all you're going to punch in. This time you're going to punch in 4, comma, 3. What's it tell you? 0.19? Part B. Still using Poissons, so keep your calculator out. This time it says at most 3. So what do we want to find? We want to find the probability. What are the possible errors on this page? How many? Could we have 5? Give me the numbers that work. 0, 1, 2. Is that it? And 3. So we want to find all those. The easiest way to do this, instead of going to Poisson PDF, go to Poisson CDF, and you go up to the highest number that you want to include. There was we were sort of confused about that at the end of the last class. The highest number that you want to include. So what do I put? Second, bars, go down to Poisson CDF, hit enter. What numbers are we going to put in? What's our mu still? 4, 3. We still put in the same thing. Should give us a completely different answer. Boy, I hope it doesn't give us 0.19 or I'm going to look stupid. 0.43. So what's the probability that there's 0, 1, 2, or 3 errors on the page? About 43% of the time.
So what was the other one where you said that you couldn't count like the highest number, but you had to go one below it?
If they, let's read what the next one says. More than 3, yeah, that one didn't tell us. Let's do this. What if they'd said, I'm going to throw one in here. What if they'd said, less than 4 errors on the page? Then when we go to put it in, our numbers, we're still going to use CDF. The mu is still going to be 4. Are we going to put 4 in here? We don't want to include 4, do we? If we want less than 4 errors, what numbers are we including? 0 through 3 again. So we want to drop this number down to 3 because we don't want to include 4. Does that make sense? So you got to, depends on how they write it. This time they wrote at most 3. So they wanted to include 3 in it. If they'd said less than 3, then we got rid of 3 and only counted 2, 1, and 0. Part C. Let's see. More than 3 typographical errors found on the page. So we have a probability that we're greater than 3. What numbers are we including there? Give me a possible number of errors that we could have on the page. Anything over 3. So give me some. 4, 5, 7, 10. Anything. Do we really want to sit here and try to figure out anything? No. So what we're going to do with this, when you get these, where it's something like this that is going out for infinity, there could be 1,000,000 on the page, right? Probably not, but if there is, it's not much of a newspaper. So what we probably want to do here is, instead of finding this, we want to find the probability that it's less than or equal to 3. And we're going to subtract that from what number? 1. They should total up to 1. So we're going to take 1 minus that. Well, didn't we just find this?
Yeah, 19%.
That was exactly 3. What was it if it
Oh,
was?
43.
So we do 1 minus 0.43, what's that give us? 0.57. There is nothing on the calculator to accumulate up. Now, next chapter, there will be. This chapter, there's not. So we find all the stuff down below. So we're finding, you know, if we're starting at 0, 1, 2, 3, 4, so on, so on, so on. And we got our it's not really a curve here, but we got our bars, you know, however they are. We're adding up all those bars all the way out through there. Well, we're trying to find from this bar over. Well, what we can do is just subtract that part there off and look at that. What should happen the farther and farther you go out here? What should happen with those probabilities that we're adding on? It should get really, really small, and they, as a matter of fact, they'll get so small that they won't matter anymore. When we get out to 1,000 mistakes, probability is going to be probably be something like 0.0000000000000. Let me keep going, Michael. 000. And if we punched it in, we could punch it in on our calculator. If I hit second vars, go down to Poussin CDF, or PDF, sorry. I hit enter, we got 4, comma. If I said 1,000 mistakes, we want to know what's the probability of getting exactly 1,000 mistakes. 1,000, I punch in, right? What's it say? 0. So the calculator says there's no chance of that. The calculator's telling me, I'm not even going to tell you what that answer is because it's so minute that you won't understand it anyway. Other questions? So if I write a problem up here and it says, find the probability that Andy Dalton completes his first pass of the game on his 7th attempt. Are we dealing with geometric distributions or Poussin's distribution? Geometric. If I say, find the probability that that Kostas Akumuto, whatever his name is, for UD, that basketball player that they got now that's not very good and he thinks he's great.
Giannis, brother.
Yeah.
His brother?
Yeah.
Is he good?
He's not as good as Giannis. He ain't nowhere close to Giannis.
5 points a game.
He's,
Giannis is nuts.
he's averaging about 5 points a game. He's averaging 5 points, but he's shooting about 50 times. He doesn't never pass the ball. He doesn't
So he
understand.
thinks he's his brother.
Yeah, he thinks he is because he gets the ball out top of the key and he wants to drive, and after 2 dribbles,
He was a
the
real
ball's
high
gone.
recruit, wasn't he?
Huh?
He was a real high recruit. Wasn't he?
Yeah, he was. Probably because of his brothers. But anyway, what if probability that in one game he makes 2 shots, given that his average for shots made in a game is 5? Would we be doing geometric or Poussin's? Poussin's, because we're dealing with average and how many in a certain game and amount of time. All right? Everybody think they can understand all that?
So it's really just the way they word the problem.
Yeah. Now, if it's a binomial,
Success and failure.
right. But the bad thing with that is, again, we just got to talk about geometric could also be just a success and a failure. But you got to realize that in a binomial, they're just saying, how many successes are there, period. Not how many successes are there in this area or something, based on a mean, right? So everybody's got all this down, right? I'm going to write some stuff down with it. You might want to write it down. I'll tell you what I'm going to do. On this test, you're not going to be allowed to use your binder on this test. You'll be allowed to use one sheet of paper.
Normal
Front and back, normal sheet of notebook paper. Yes, I don't want you bringing in some big
So like
poster board.
this board,
Yeah.
does it matter what's on it?
Nope. Probably shouldn't even have said that. None of you probably wouldn't even thought about it, right? None of you guys are Cole Yancey. That's what he'd think of. He'd think of something like that. He's pretty, when it comes to getting around things, Cole was one of the best students I've ever had as far as, well, you said this. Yeah, I guess you're right. I didn't specify. So on this, discrete random variables and continuous. Remember, discrete, you got to be able to tell the difference. This is something we did back at the start of the chapter and it wasn't very difficult. Discrete, something you can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Continuous, something you can't really count. 5.2, 5.3, 5.45, 5. So continuous is something that's sort of measured, probably. Something that you'd have to measure. As far as continuous goes, did we deal with continuous anymore after that first section? That's next chapter. All right? All you had to be able to do was decide if something was discrete or if it was continuous. Now, the discrete, we went over all those throughout the chapter. Is it a probability distribution? Remember, to be a probability distribution, two things got to be true. All probabilities, sorry, I wrote in cursive. All probabilities between, not between, all probabilities 0 to 1. All probabilities have to be 0 to 1. So if I told you this was our probability, 5/3, what would you tell me? That's not possible. All right, so if you see a probability that's larger than 1, not possible. What if I gave you this as a probability? -1/5, not possible. All right, the second thing for something to be a probability distribution that has to happen is all add up to how much? 1. All of them got to add up to 1. All of them have to add up to 1. As you're writing some of this down, if you're going to use this sheet of paper for your test on Friday, what's some other things you might want to put on there? Maybe some examples, maybe the calculators, things, the formulas that we're going to write down here in a few minutes for a lot of them, maybe the calculator steps, whatever. Stuff like that, just to give you some ideas. Make a probability distribution in its graph. I'm going to do this real quick. See if I got a free slide. Of course not. Previous. Ignore this. Remember, with the probability distribution, I'm going to draw this chart. Oh, you stupid thing. With the probability distribution, what you have is you have your x values down through here. With the probability distribution, you just have x and p of x. But you could put f in there, which is your frequency, p of x. That part right there is a probability distribution. Notice I made it go out there farther because what am I going to do to this chart here in a couple minutes? add on to it, because we had a whole bunch more stuff. Now, I think there's one problem on the test where you actually have to make the chart and find the stuff that way, and then all the rest of them, if you wanted to use your calculator to find the mean, standard deviation, and all that stuff, you don't have to make the whole chart. But I think I put one on there where you have to. So this part right here is just a probability distribution. The other part of this one says, and its graph. What's its graph going to look like? Let's say what? Histogram. And on that histogram, you're going to have the x's along the bottom, and you're going to have your probabilities along the side. So like 0.15, 0.20, 0.25, 0.30, so on, so on, so on. I know there's a problem on there where you have to make a histogram also. Be able to find the mean, variance, standard deviation. Mean, variance, standard deviation. I know you can't read any of that, but of a discrete probability distribution. We probably want to write down those formulas, right? So let's find them here. For a mean, we'll find the mean of a probability distribution. Do we have a formula? Yeah, there it is. I'll tell you what, I'm not going to write down the formulas for this one, because this is the one, if we're going to do it using the formulas, then we have to make that long chart. And that's what I'm going to do. I'm going to go back to the chart. So if we go back to the chart, our next column that we want here is x times p of x, the probability of each one. I probably should have said, how do you find the probability if our x is 2 or 1? How do you find the probability here? Take all these, all the frequencies, add them all up, divide how many of the ones occur by that total number. So this divided by the total. I'm going to draw this down here. We need this total here. Every time you need that summation. Then when we get to here, we need that summation. If I remember, what's this? When we add all these up, what's that equal? That's the mean. This one here equals what? That one should equal 1. This is your mean. X times P of X. So you find X, or they're going to tell you X probably on each one. P of X, multiply, write those answers in there, add them all up, that gives you the mean. Next part of our chart, to help us find the variance and the standard deviation, we do x minus mu, x minus the mean. If I remember the next part, x minus mu squared. Notice I'm not adding any of these up. The only one that you really need to add up, you need to find the mean here. This one should add up to 1. You can check yourself to make sure that you did stuff right. The frequency you need to add up just so you can find the probabilities. Then the next one, if I remember that one. It's the probability of each one times that right there. That's why we just found that. Times x minus mean squared. So we're going to take this column times this column, each one. Write those answers down there. Then we're going to add all those up. If I remember what that equals, that's the variance. That's the variance. Remember, we find variance first when we're doing it out the long way. We find standard deviation first when we're using the calculator, because the calculator knows, hey, variance is about a worthless number. All that helps us do is get to the standard deviation, so it doesn't even show you that.
So we can do this, like find those on, like doing the graph.
And we're gonna do it here in a second. What do we do to find the standard deviation?
Square root.
Take the square root. So for standard deviation equals the square root of the variance. Square root of the variance. So once you find the variance, you just take the square root of it. So that's this chart. If we had this chart, let's just make up some numbers here real quick, and we'll do what Katie wants. We'll go 1, 2, 3. We're only going to do 3 numbers. And we'll say for 1 there was 5, for 2 there was 7, for 3 there was 2. We add all these up. What's 5 plus 7 plus 2? 14. To find each probability, we take this number divided by that. What's, somebody have your calculators out so you can help me. What's 5 divided by 14?
0.35.
2.5?
2.9.
3.5? 0.35. What's 7 divided by 14? 0.5. What's 2 divided by 14? 0.14. What should all those add up to? They should all add up to 1. Ours don't. Ours adds up to 0.99. Is that all right? Yeah, it's probably pretty close. You might want to be a little more precise. We're not going to. Then our next step here, we're going to take this column times this column. 1 times 0.35 is 0.35. 2 times 0.5 is 1. 3 times 0.14 is what? 0.42? Is that right? What do we do with all those? Add them all up. 77, 1.77. So what's our mean? 1.77. That's our mean of this thing. So again, and not only is that the mean, that's also called the expected value. That's what you expect to occur. So if I'm picking whatever it is here, 1, 2, 3, I expect to get about 1.7, 1.8. Then I take our x minus our mu. This number minus this. X minus, oops, I'm sorry. Not this number minus this. This number minus the mu, right? So negative 0.77. I messed that one up. 0.23. 1.23. Don't do what I just did and subtract this. You're subtracting x minus the mean you just found. Then you take each one of those numbers and you square. What's going to happen when you square that negative? It's going to become a positive. What's 0.77 squared? 0.59. 0.23 squared? 45? 47? Which one? 47? Is that wrong?
We squaring it?
Yeah.
Oh, wait, I'm
I got 0.05.
0.05?
sorry.
That's right. 0.05. That one was 0.59, right? Yeah. 0.77.
3.13.
Are all 3 of those right? Now we take this column times by that column. What's 0.35 times 0.59?
Wait, the bottom one's 1.5. I was about to say.
1.5?
That's line 10.
The next one's 0.2.
That's these 2 times together? 0.2065. So 207 we'll say. We'll go out 3 places. What's 0.5 times 0.05? 0.025. 0.21 is the last one. Now these we do need to add up, so we get what, 0.43442. Is that right? 0.442.
Yeah.
What's that number? That's our variance. Then the last thing we got to do is find the standard deviation. How are we gonna find the standard deviation? Take the square root of that. 0.66. So we got variance, standard deviation, mean. That's for just a probability distribution. For a binomial distribution, were they that difficult? We had little formulas, right? For a binomial, the mean is n times p. And that's all you had to do. The standard deviation, or the variance, was n times p times q. And we'll talk about those formulas here in a minute. Now, what Katie asked is, well, could we just use our calculator? What do we have to do on our calculator to do this?
Definitely listening, right?
We got to do the list. So what are we going to put into the list? 1, 2, 3, and then the probabilities in the second list. All right? So if we punch that in, we go to Stat, Edit, go to one of your lists. I don't have anything in mind, so that's good. I punch in 1, 2, 3, go over to the next. Go over to the next list, punch in 0.35, 0.5, 0.14. So we have both those in our list. Then what we do once we have them in the list is you go back to, what do we go to? Stat, calculate. What do we punch in? Anybody remember this one? Stat, calculate. Hopefully you got that list of calculator steps around somewhere that I passed out, right? I think you hit 1 bars, and then you put in second, L1, or whichever list you put it in, comma, L2. So 1 bar stats, then you put in the both lists, L1, comma, L2. What's it pull up? What's it tell us our mean is? 1.7, mine says 8, but it's close enough, right? And then you look on down and it tells you your sigma x is 0.67. Is that what we came out with? Yeah, pretty close, 0.66. Now what does it not tell you? The variance. So if we had to find the variance, what would we do with this 0.67 on the calculator? We square it. We go backwards, right? So we just do 0.67, square it, and you get 0.4489. That's pretty close to what we
How do
had.
you get the list? How do you get
You hit Stat, calculate. We do the 1 bar stats again, and then you punch in whichever 2 lists divided by a comma. So you have to hit, like I put mine on the first and second list. So I hit second, number 1, comma, second, number 2, hit enter. Got it? So making the chart, doing it on the calculator. You got that list of steps on the calculator. I passed that out at some point, right? Passed out like 3 of them this chapter. Should have it somewhere there, or you wrote it down. Maybe I didn't pass it out, maybe I wrote it down, or had you write it down. I'm pretty sure this one I passed out. So I probably passed you out something that looked like that. All right, so try to find it. If not, it's on the notes somewhere. That's for just a probability distribution. Go back here. Decide if it's binomial or not. What makes something binomial? Oh, I'm sorry, expected value. Expected value real quick, same as what? That's the mean. Expected value and mean are the same thing. So when you find the mean, you found the expected value. What makes something binomial? It only has what? 2 outcomes. It only has 2 outcomes. So rolling a die, is that a binomial? No. Flipping a coin, is that binomial? Yeah. Be able to find binomial probabilities, Make a binomial distribution. Binomial distribution, again, same thing as the other. Probability distribution, you got your outcomes and your probabilities. Its graph, what's its graph going to be again? Histogram again, same idea.
So it's the same thing as we just did.
It's same thing except how many outcomes do you have? Two. You only have two instead of 5, 6, 7 outcomes, whatever they are.
We only have two X's.
So you just got X and P of X for the distribution?
So it would be something like,
Actually, like
X.
1, 2 maybe, yeah. Now, we didn't make a whole lot of, I probably wouldn't even ask you to make the distribution there on a whole lot of stuff because we didn't do a whole lot of that because there is only 2. So you got 1, 2, 1's probability, 2's probability. It doesn't, I mean, I guess you guys might like it if I did that because they'd be pretty short, right? The formulas. The formulas, if you're trying to find the probability for a binomial, I'm going to write this formula down because I think Ms. Clark said last time, or a couple times ago, whenever it was, she liked to use the formula. So I'm going to write it down. This is for binomial, yes. That's how you find the probability in a binomial. Now remember with binomials, when we were finding probabilities, we weren't just finding 1 and 2. I shouldn't have said that earlier. It's not, now that I think about it, that's not the way I meant it. When we're finding probabilities, we're figuring out for a binomial, how many times does this occur? So if you're taking a true and false test, and it's got 10 questions on it, and you just guess on all of them. How many times do you get 4 right? How many times do you get 5 right? So our X's aren't just 1 and 2. Our X's are how many successes are there? All right? So the X's are how many successes there are on the binomial. But that's the formula. If you want to use the formula, that's fine. Otherwise, what are you going to use probably? What did we use most of the time? Use the calculator, right? Where do you find this stuff at on your calculator? Remember, for all this stuff from here down, you find it second, then what? Second bars. Second bars. For these, for a binomial, we just said this a minute ago, for a binomial, the mean is just n times p. So we don't have to go through all that big chart and everything else. For a binomial, mu is n times p. Variance is n times p times q. And standard deviation is the square root of n times p times q. So for a binomial, you have to find those numbers right off the bat. Have to find n, you have to find p, you have to find q. Remember, how do you find q? 1 minus p, 1 minus whatever the probability is. Geometric distribution, with the geometric distribution, what's going to be a key to tell you if you're doing a geometric distribution? You're what? Give me something that,
Yield mean.
yeah, that's the other one.
The success, or how many times it takes for one success.
First success. So if you're looking at where does that first success come from, that's the geometric. And then what's gonna be a key to tell you if you're using Poussins?
Find some, a specific thing.
All right, how many's in a certain area or something, and it's probably gonna give you a mean. It's gonna tell you what the mean is. All that soaked in, Camden? Apparently not. It's not working very well, it's not stable. All right, perfect. See Sydney in?
Yeah.
On this, want to do some problems off this real quick. Anything up here that you want to really see me work because you're confused about it, and I'll try to find a problem on this real quick.
Can we use it with this?
Yeah, I probably let you use the charts too. I'll be writing a whole bunch of crap on them, trying to cheat.
On the test, are we gonna have to use like the formula or can we just plug it in?
Most of them probably unless I specifically say use the formula, which I don't think I do on any of them. Some of them though, I might want you to make that chart. Nobody sees any that they want me to do real quick?
Something to do with Sana.
Something to do with what?
Sana.
Poussin?
Yeah.
There's one on the very back. You want me to do one of those two?
Sure.
So 31. On this one, they actually tell you to use Poussins. Car towing service company averages 2 calls per hour. So that's the mean, right? Mean is 2. Determine the probability randomly selected hour that they get 6 calls. So probability that we get 6. We could use the formula. You want me to use the formula or do you want me to use the calculator? Calculator. So in the calculator, all we're going to punch in the calculator, we're going to go to second bars. Then we're going to go down to Poussin. This time we just want PDF because we're just finding exactly 6. And we're going to punch in the mu, and then we're going to punch in the 6. Anybody get that so I don't have to punch it in my calculator? 0.012.
Yeah.
Anybody else get that? Yes, no, maybe? So what's true about that event? How often is this towing company going to get 6 calls in an hour?
Very.
It's not very likely, is it? All right, so if it's less than 5%, then it's unlikely that it's going to
We
happen.
have to put that's unlikely.
No, unless they ask you. If they ask you, is this event likely or not, then you have to put. Or on the other things I didn't talk about, they might ask you, is this skewed left, skewed right, whatever, or symmetric. They might ask you that also.
What you say the difference between PDF and CDF?
PDF is if we're just looking for that certain event. CDF, watch what happens if we do CDF with this one. If we punch this into CDF, where we want everything less than or equal to 6, what do you think the probability is going to be? It's going to be very high because their calls, are they going to get less than 6 calls in most hours? Yeah, 6 or less. So if we punch that in, we go second bars, go down to Poussin, and this time we go down to CDF. We put in 2 for the mean, comma, 6, close the parenthesis, and I get 0.995. So we get a big probability if we're looking at everything at or below 6. We get a small probability if we're just looking at how many times they get exactly 6 calls.
Alright, so you said discrete is when you can count, so you can count the numbers of coffee, cups of coffee sold. Right, so you can
Well,
count-
the numbers of cups
Well, it
of
says
coffee.
The number of cups of coffee sold can
Yeah.
count that, so that's discrete.
So that'd be discrete. But
And
if you
then-
were talking about coffee in the cup, then that would be continuous.
Okay, and then it says the height players on a basketball team, you can measure that.
So that would be continuous.
Okay.
If you have trouble getting to that video, get a hold of me.